Yeah, then I will start. Good afternoon, everyone. I'm Jun-Jing from Hangzhou Dianzi University. I would like to present a brief report on predicting creep rupture in austenitic steels with mechanism-based fundamental models. And this work is conducted together with Professor Rolf Sandström from KTH. Yeah, first introduction. So the creep rupture is a critical issue in high temperature materials and structures. And the creep experiments in real life can take 30 years or more. So the models are required to predict the long-term creep life. And in general, there are two types of creep models. One is the data-driven models, like the empirical or semi-empirical models, and also the recent machine learning models. And they are featured with the fitting or adjustable parameters. And they also have some advantages and limitations. And another one is the mechanism-based fundamental models. And it aims to bridge the microstructure and the defect evolution to the creep properties by using the mesoscale series. And for the data-driven creep models, there are many publications available. And in our recent work, we have also proposed the physics-informed TTPs, like the Larson-Miller TTPs, and also physics-informed machine learning. And these models have been widely used in various metallic materials. But this is not the current topic. The topic now is focused on the mechanism-based basic creep models. It's expected to review the underlying creep damage mechanisms without adjustable parameters. And here is a flowchart for the design of the basic creep models. That starts from the computational basis with like the first principles calculations and the thermodynamics to the microstructure parameters like the elastic properties. Then go to the mesoscale theory like the dislocation, precipitation, and the solid solution hardening. Then one can model the ductile creep rupture. And in addition to this, we also consider the creep cavitation along the sliding grain boundaries, and which will result in the brittle creep rupture. And by combining these models, it's possible to generate the final mechanism-based fundamental creep theory and models. And then we go to the creep models. Since grain boundary sliding is the basis for both the creep cavitation and the brittle creep rupture. And in our recent work, we have established a systematic grain boundary sliding database, and it covers a very wide range of materials and conditions, including the pure metals and their alloys and steels. And this database, it covers 70 years of references and also a very wide strain range and the grain size temperature range. To model the grain boundary sliding, we proposed a physics-informed machine learning, and here it's a flowchart. First, that's from the data preparation. We consider the different variables such as the strain, grain size, and the substructure. And by incorporating the constraints with the machine learning algorithm, so we can generate the final physics-informed machine learning. And on the other hand, the theoretical grain boundary sliding models was also analyzed. And by combining both, we can generate the final basic grain boundary sliding models. It was finally in a very straightforward form. It's proportional to the grain size and the strain, and all parameters here, they are well defined. Here are the results for the grain boundary sliding models. Now we can see that the model can predict the green boundary sliding for various materials and also covers many different conditions. In addition, it can also be applied to the three creep stages. That's the primary, secondary, and the tertiary creep stages. And on the other hand, for the physical parameters in the basic creep models, we use the multi-calc to simulate the precipitate evolution, such as the particle radius and the phase fraction as a function of time in SR3C studios. And also the first principle methods, we used the EMTU code to calculate the physical parameters like the elastic properties and the line misfit. And this parameter is crucial for the solid solution holding. And then we can go to the ductile creep models. And in this model, we consider the dislocation mobility and the precipitation hardening, and also the stocking fault energy effect and the solid solution hardening, which is related to the line misfit. In addition to the ductile creep models, the brittle creep rupture due to creep cavitation along the sliding green boundaries was also modeled, and this involves the green boundary sliding models and the creep cavity nucleation and the growth models. And then with all these models available, we can predict the creep rupture of the materials. Now here, the three figures above, we shows the prediction from the fundamental creep models. The data points here are experimental data from different sources, experimental sources, and the lines here, they are the prediction results with the ductile creep rupture models and the brittle, and also a combination of both. And the three figures below, this shows the corresponding regression analysis for the predicted creep rupture time versus the experimental creep rupture time. And in general, there are no significant differences between the statistical analysis for the three ways. Both the regression coefficient and the regression slope, they are quite similar. But we can identify that, for example, at lower stress and higher temperature levels, the brittle creep rupture dominate. Yes, and then this summary, the mechanism-based fundamental creep models, they can predict the creep rupture of austenitic steels. We have just shown one example for SR3C steels. It can also be applied to 304 and 347, 360. Well, compared to the data-driven methods, they may not be perfect predictors, but they provide insight into the underlying creep failure mechanisms, including the dislocation, precipitation, solid solution hardening, stocking force effect, and the creep cavitation along sliding green boundaries. So they are critical for the reliable long-term creep life prediction. And in the end, I would like to recommend an open access creep book by Professor Rolf Sandström. It's a very good book about the fundamental theory and modeling for creep of metallic materials. That's my very brief report, and thanks for your attention.